I want to do another example question now. This is more of an application of multi-force problems. We've looked at multi-force problems, right? In fact, we've had a quiz on multi-force problems, but this is more of an application. Your example number 7 is going to be an application that we call elevators, right, or things like elevators. Example number 8 is going to be another application. It's going to look a little bit different, but bottom line is they all boil down to the same thing. They're multi-force problems where we have to draw a free body diagram and then say F net is equal to the sum of the forces. When you're in an elevator and you accelerate in the elevator, you will either feel lighter or heavier. You've felt that before, right? When you're standing in that elevator and it takes off, accelerating upward, you feel heavier for a brief time. As it begins to accelerate, you feel heavier. Now, once it moves at a constant velocity, evens out, moves at a constant velocity, now you're in a state of equilibrium, which means the forces balance and you feel like you weigh the same as you really are, right? But when it accelerates upward, you feel heavier. When it accelerates downward, you feel lighter. Now, let me explain why. What you feel and perceive as your weight isn't your actual weight. My actual weight is about 700 newtons. That's in newtons, right? In pounds, it's like 155-ish, whatever in pounds. But in newtons, it's about 700 newtons. Now, what I perceive as my weight is usually 700 newtons, but not always. When I'm in an elevator accelerating upward, I might perceive my weight to be 750 newtons. Or when I'm accelerating downward, I might perceive it to be 650 newtons. I perceive my weight sometimes different than my actual weight. Why? Because the weight that I perceive is actually not my weight. The weight that I perceive is my normal force, the force of the elevator floor pushing up on me. That's what I want to find in question number 7 here. As this man stands in the elevator, accelerating downward at a rate of 2 meters per second squared, what's the normal force? The force of the elevator floor pushing up. Now, I'm going to draw a free body diagram of this man in the elevator. Doesn't have to be complicated. I'm going to say the force of gravity is acting down on this man. What other forces are acting on this man? The weight, did you say? The weight is the force of gravity. So we've already listed that one here, the weight of the force of gravity. What else acts on this man? There better be something. The normal force. If the normal force does not act on him, what happens to him? He plunges to his death, to his certain death. Because he would accelerate downward at 9.81. Think about that. If the only force acting on him is gravity, he's going to free fall. It's like jumping off a cliff, right? He's going to free fall. That's not very good. There is a normal force acting up. If he's accelerating downward, is the normal force bigger or is it smaller than gravity? Somebody said smaller? Why is it smaller? Why is the upward force smaller than the downward force? Not because he's going downward, because he's accelerating downward, right? If I have the normal force equal to gravity, he could still go downward at a constant velocity. That would be a state of equilibrium, right? Balanced forces, constant velocity. But if the normal force is smaller, the upward force is smaller than the downward force, of course it's going to accelerate downward. Okay, let's do our thing. We know how to do this, right? F net is equal to the sum of the forces. In this case, we're going to say Fg plus Fn. In most of the questions that we've done so far, it's been F1 plus F2 plus whatever, whatever, whatever. Here it's Fg plus Fn. Next step is m times a is equal to Fg plus Fn. Now we sub numbers in. The mass of the man is 73 kilograms. The acceleration of the man is what? 2.0? 2.0? Negative 2.0. Why? Because it's accelerating downward, right? Fg is, that's going to be 73 times, what's g? We're going to say negative 9.81. The force of gravity, look, this force of gravity here is negative because it acts downward. I don't care whether you put the negative in front of the 9.81 or put it in front of the 73. It doesn't make any difference. That force needs to be negative because that force is downward. The only thing we have left is the normal force. What are we looking for? The force of the elevator floor. Is that not the normal force? Yeah, it is. So let's figure this out. 73 times negative 2 is negative 146. 73 times 9.81, oops, 73 times 9.81 is what? 716.13. That's negative plus Fn. I'm going to take the 716.13 over to the other side by adding, right? It's a negative on the right side. I'm going to take it over to the other side by adding. So it's going to be negative 146 plus 716.13, 0.13, I should have said, which gives me a value of 570.13. How many digits should that be? Take a look at your data here. This is 2 digits. This is 2. Final answer should be 2. So let's underline the first 2. Third one is a 0. Do we round the second one up or down? Down. So we're going to say it's 5.7 times 10 to the 2 newtons. So the force of the elevator floor pushing up on them is 5.7 times 10 to the 2 newtons. We could also call that the normal force. We could also call that, listen carefully guys, we could also call that the apparent weight. Not how heavy he is, but how heavy he feels. He would feel lighter than he really is because he's accelerating downward. You can imagine, guys, if you free fall, how many people have ever been in one of those free fall rides at an amusement park, whether it's at Galaxyland or, yeah? When you're free falling, you feel weightless, right? If you hold something in front of you like a heavy, like a little rock or a coin or something, and then you let it go as you start falling down, guess what it does? It falls right down in front of your face the whole way. Why? Because it's weightless, or it appears to be weightless according to your frame of reference. How come? Because the normal force acting on it is 0. Got it? We feel the normal force. Our real weight is gravity, but our perceived weight, our apparent weight, is the normal force. Yep. What's the man's actual weight? His actual weight is just the force of gravity, right? So the force of gravity is just m times g. We're going to say it's m times the absolute value, because technically it's negative, but when we talk about weight, we don't usually think about a negative weight, right? We just call it positive. So let's say it's mass, which is 73 times positive 9.81. Gives me a value of 716.13. We're going to round that to 2 digits. That's going to be 6 rounds up, so the 6 is bigger than 5. So the second digit is going to round up. It's 7.2 times 10 to the 2 newtons. Does that seem reasonable? Your weight is 716 newtons. You feel like you weigh 570 newtons. You're accelerating downward. You feel lighter, right? If you accelerated downward at 9.81, because you were free falling, you would feel weightless. You ever see video of the astronauts in the International Space Station orbiting around Earth? Don't you think it would be kind of neat to be weightless, to have 0 weight as you're swimming around in space? Do you know that their weight is not 0? We call it microgravity, but it's a little bit misleading. Their weight is not 0. It's not even close to 0. Their weight is about 90% of what it is on Earth. Their weight doesn't change dramatically. They just appear to be weightless. Do you know why they appear to be weightless? Do you know why they feel weightless? Because this is the Earth. If this is the space station, it wants to go in a straight line, right? but it can't go in a straight line. How come? Because gravity pulls down on it towards the center of the Earth, right? So where does the space station go as a result of that? It falls. It falls like a projectile, right? It falls downward because of gravity. But it's got inertia taking it out to the right, so it ends up going like this. And then it falls. So it ends up going like this. And then it falls. And then it ends up going like in between like this, right? So the space station is constantly free falling. You're on the space station for 6 months, it's being like on that free fall ride, like the Drop of Doom or the Guardians of the Galaxy ride at Disneyland for 6 months, nonstop. You feel like you get sick when you're on that ride sometimes, right? But that's only because you're on it for 3 seconds. Like you free fall for 3 seconds. That feeling kind of disappears after you're on it for a couple months, I guess. You kind of get used to it. You're not weightless. You just feel weightless because you're free falling. You're free falling towards the Earth constantly. It's just by the time you free fall to the Earth, guess what? The Earth isn't there because it's curved away. Make sense? Gravity here is about 9.81. Gravity here is about 9. It's not much different. It just feels weightless. We call it microgravity, but it's not really microgravity at all. It's almost regular gravity. It just feels like microgravity. Make sense? Oh yeah, I didn't even realize I was still recording that actually. Oh well. What's the man's apparent weight? Answer that one for me quick. 5.7 times 10 to the 2 newtons. All right, let's have a look at a few questions on worksheet number 12 here. Specifically, for now, I want you to do questions 1 to 5. Now, know that these questions 1 to 5 aren't all elevators. Question number 5 is a chain, but it's a vertical problem. Instead of the floor being the normal force, it would be the chain that's the normal force, right? It's the same analysis, just a slightly different context. So you're going to work for the next little bit in class on worksheet number 12, questions 1 to 5. Let's take a look at number 2 here now, everyone. It says calculate the force of the elevator floor pushing up on a 50 kilogram person in an elevator that's accelerating downward at a rate of 2.00 meters per second squared. The elevator floor, we could also ask you the same question, but phrase it a little bit differently, ask you for the normal force, or we could ask you for the apparent weight of this 50 kilogram person. They'd all be the same question, right? Solving for the force of the elevator floor. Draw a free body diagram. Here's the person in the elevator. Here's the force of gravity acting down. Now, is that normal force going to be bigger or smaller than the force of gravity? What is it? The normal force is bigger? Is smaller. The normal force is smaller. Good. The normal force is smaller. We know that because it accelerates downward. If it accelerates downward, the downward force has to be bigger than the upward force. If it accelerates upward, the upward force has to be bigger. If it moves at a constant velocity, what do we know about the forces? If it moved at a constant velocity, it's in a state of equilibrium, and the forces would balance. Right. So let's say F net is equal to the sum of the forces, Fg plus Fn. M times A is equal to the sum of the forces, Fg plus Fn. M is 50 kilograms times the acceleration is negative 2.00. Why did I make it negative 2? Because it accelerates downward. Okay, not because it's moving downward, because it accelerates downward. If it was going downward at a constant velocity, what would the acceleration be? 0. Right? If it was moving at a constant velocity, like question number 4 is, we'd say the acceleration is 0. But here it's negative 2. The force of gravity is 50 times negative 9.81. Again, negative in front of the 50, negative in front of the 9.81. It doesn't matter where you put it, as long as that term is negative, because gravity is acting downward. And we're solving for the normal force here, the force of the floor. 50 times negative 2 is negative 100. 50 times negative 9.81 is negative 490.5. Now, we're going to take that 490.5 over to the other side by doing what? How do you take it over? Somebody said it? John? Yeah, it's a negative on the right-hand side, so we're going to take it over by adding. Hold on for a second, guys. We get 390.5. Hold on, please. Now, why don't I divide it by 490.5? Because it's not attached to the Fn, right? If it was 490 times Fn, I'd divide it. But it's not. It's negative 490 plus Fn. So it's really like saying Fn minus 490. Take the 490 over to the other side by adding. So we get 390.5. Hold on, please. Gabby, have a seat. How many digits are we going to round this to? This is 3. This is 3. Final answer should be 3. So that's a 5. The fourth digit is a 5. The third digit is going to round which way? Going to round up. So this would be 391. 391 newtons. Does that make sense? All right. Finish those 5 questions up for homework if you haven't done that already, please.